And now we start with the first truth section here in Applications Engineering. Last lecture we just have done some repetition in signals and systems. Just one remark, there is now a situation which is not the best because the seminar has shifted to Wednesday, 9 o'clock. This means the seminar is before the lecture, so this is not so nice. Yeah? But I cannot basically change the lecture with the seminar because I have a lecture at the same time. It's impossible. So you will see in the next seminar, yeah, I basically introduce new questions in this task collections, which are related to a topic which I address very shortly later, okay? But you still work with these tasks. This is, the topic is basically correlation functions of deterministic signals, yeah? But this is quite simple to understand because it's, there are some definitions, yeah? And I put it basically the definitions in this new task, yeah? And you see a table, and this table shows all these required definitions, yeah? And then my advice is that you start with these tasks, yeah? And then I can discuss in the next lecture description of stochastic processes, and I don't want that you start in the seminar with stochastic processes before you have about this in the lecture. Okay, this is, in my opinion, important. Yeah, so don't wonder if there are problems with these tests, and you say, I don't understand it all, then we have to find another solution for this. Yeah, this is not optimal that the seminar is before the lecture. So now we start. So this section is Yeah, I use on the slides a longer name, but it's the same topic, of course. Yeah, in the on the slides you can read the how's it called on the slides? The description, representation of bandpass signals. Here you can see it, and systems in the equivalent low-pass range. Here I use an abbreviation, yeah, to save time and say bandpass. It's the same topic. Yeah, there are different names. Low pass, transform. So, and I just start with a simple motivation. Yeah, do we need this? And then you will see motivation, or even in this lecture, you will see this is not just math, just a model. You can use it in practice. Motivation. Let's say we want to model a fiber optical system and the signals. And we are talking about single mode fibers. Single mode fibers require laser diodes as a transmitter because these laser diodes know this. They are characterized by which feature? What is the basic feature of a laser diode compared to a light emitting diode, for instance, or compared to any natural light? What is the basic property? What would you say? Laser diode. Yes, it is, but this is just a result of this property. The light which is emitted is coherent. Yeah, that over a longer time, in the best case over an infinite time, yeah, there is no phase change basically. So it, best case, yeah, it just emits monochromatic light. So pure, you know, light has properties from quantums. So you need quantum mechanics, also from waves. Yeah, so it's a wave. Let's say, take a look at a wavelength of This is typically used for single mode optical fiber systems of 1.5. Yeah, this is the wavelength. Now, instead of using the wavelengths, because, yeah, I mean, if you have a wave, yeah, you can substitute basically wavelengths by the frequency, transmission speed. Now we can say, okay, that the carrier frequency of such a laser diode, let's say carrier frequency, laser, so of this is a laser diode, yeah, and we take a look at now at the corresponding frequency, carrier frequency, and this is nearly 190 terahertz, not gigahertz, terahertz, so it's optical frequency. Yeah. On the other hand, if we take a look at, assume, yeah, we take a look at an ideal monochromatic wave. So it's an ideal laser which just emits monochromatic. So it looks like a sinusoidal signal if we take a look at the field strength, yeah, at the field in the optical domain. This means that 1 by Fc, so one period sinusoidal wave is nearly 5 femtoseconds. Yeah? So it's 5 times 10 to the minus 15, nearly. It's just that you get an idea how large this carrier frequency is and how low this period of the optical. Now let's say we want to model this system, and you have this huge frequency, but we want to model the signals, yeah, and it's at least not efficient, let's say, yeah. If you want to draw a signal, how does it look like? How do you want to draw this? Let's say the bit rate is 10 gigabit per second, which means the bit interval is 0.1 nanoseconds, but these 0.1 nanoseconds are huge compared to these 5 femtoseconds of this period. And the idea is we need to model, to do this efficiently, the system not in the original frequency range, we do it in the so-called equivalent low-pass range. Concept behind this is quite simple. And we do this not only for the signals, we do this for the whole components. So, in order, yeah, to, let's say, allow an efficient modeling of, there's only one, of the signals and system components. Let's say laser, fiber, photodiode, whatever, yeah? We model all these things, the equivalent this means we ignore this huge carrier frequency, yeah? And if we do this, this is a transform what we are doing. With respect to this carrier frequency, it seems that our signals have a carrier frequency of 0 hertz. See what happens. Now we start. We start with a transform of the signals, 1.1. So we would now be able to model such a fiber optical system, for instance. But you do the same for radio frequency systems, for instance. This is where you need this. Always, if you have bandpass signals, yeah, it's a good idea to ignore the bandpass characteristic of the signals and to shift everything in the frequency domain. So transform. So we start with signals. For signals, there is a small difference if we later take a look at the systems, which are always assumed to be linear for signals. So transform for signals. And we start, let's say, we start with an example. Example. Of course, I don't need to say this, yeah? Real valued. Because our time domain signals in reality are always real valued. We can measure them. These are continuous time signals, yeah? We want to measure them of a real value, deterministic, bandpass signal. And if you take a look at deterministic signals, they can be energy signals or periodic signals. Here we take a look at an energy signal. For this example, I mean, if it would be periodic, then the corresponding Fourier transform would be discrete. So you would only have discrete spectral components. Yeah? You could see it in the spectrum. So we start with an example of a real value deterministic bandpass signal. Let's say we denote this as x of t, which is an energy signal. So it could be a bandpass pulse, yeah, in a time domain, which is an energy signal. That is, if we take a look at the system theoretic energy of this x of t, yeah, it's limited. For a periodic signal would, because it has an infinite length in theory. So we could say x is equal to the integral from infinity to plus infinity. Then I can write here x squared of t. So in x square of t dt would be, if this is in volt, let's say, volts, squared voltage, yeah, this would be instantaneous power, let's say, yeah, and then integrate a power, yeah, from minus infinity to plus infinity, so I get an energy, and this should be smaller than. So then it's an energy signal. But again, if this x of t is a voltage, yeah, and this is not an energy in physics, it's not in watt, it's in volt squared. This is so-called system theoretic energy. Yeah? There's no problem to this. At least the real-world energy is proportional to this energy. Now let's assume that we can write x of t, let's say. Fourier transform of this x of t is just x of f. And I write again here, because this is really important, our time domain signals is real valued, are real valued, always. We can measure them. These are analog signals. They need to be real valued. At least I've never seen the square root of -1 for an analog signal. So, and now we can discuss the properties of this x of f. Properties of x of f, and these are really important. T's x of f. These properties are, say, basically we need one major property, and this is x of f. If we take a look at positive frequencies, this is the same as x of minus f conjugated. So the spectrum of a real valued time domain signal has always this complex conjugated symmetry. And of course, we use a two-sided Fourier transform So we use, basically, if we decompose our signals into harmonic waves, we use complex waves. There are always pairs of these frequencies. One complex wave here has a frequency, let's say f, and it's never alone. There needs to be another wave which has a frequency minus f. They belong together. Therefore, in order to obtain a real value time domain signals, the weightings of these complex oscillations need to be complex conjugated. And then you can say, okay, what does it mean? It means that, let's say, the magnitude spectrum is always an even function, always. So this is not a random variable. I denoted my signal as x of t, yeah. Spectrum as capital X of f. And, sorry, this is trivial, say minus f. So the magnitude spectrum is always an even function. Could also say that if I take a look at the phase of this spectrum, yeah, I mean, I can write this as is equal to x of f magnitude e to the power of j phi of f, okay? And of course, this phi of f, if we take a look at the right-hand side, for instance, of the frequencies, this is minus phi of minus f. This is always an odd function phase. What does it mean? All this means, yeah, that basically the left-hand side of the spectrum, so for negative frequencies, this is redundant, yeah, but it's required because we need to generate, by this inverse Fourier transform, a real time domain signals. So, sorry, so what specified screen unit? Micrometers. Sorry, I go back. There was a question. This is micrometer. Micrometer. Can't you read this? It's micrometer. 1,500 nanometers. Okay. So, and we can proceed even more. Just shows from mathematical point of view, yeah, the left-hand side spectrum is redundant if we know the right-hand side spectrum and vice versa. So we can construct this if we know only the part. You could also say, now we use a certain notation. And this is really important that you understand this notation. Otherwise, you stupid results. I just say I denote the real part of this spectrum, of this Fourier transform with a prime. This is not the first derivative with respect to whatever. This is just real part, right? Thus, j times the imaginary part. I don't want to use indices here, yeah, which are very long. I just want to have this compact notation. Yeah? So in this context, if I use one prime, it's real. If I use two, it's imaginary. Then if we take a look at this real part of the spectrum, then this is, of course, because you see only here we have the complex conjugated. This is again an even function. And the imaginary part, of course, this is an odd function. Minus, yeah, odd, as the phase is an odd function. Always assuming real valued original signals in a time domain. This is quite simple. Now, proceed. Now we draw a figure of this Fourier transform, so of the spectrum, yeah, of our original energy signal x of t. So let's say we do this now. So it could look like this. So here, this is the bandpass signal, what I draw here, yeah. But in the frequency domain, of course. Now let's say if this would be an optical signal or so, this, let's say we take a look at carrier frequency Fc. This is a huge frequency in the optical communications, 100 terahertz or so, yeah? Let's say if we do radio frequency transmission, we talk about Wi-Fi, it's 2.5 gigahertz, for instance. So, and we see the same on the left-hand side. Here we see minus FC, let's say. Yeah? So, and now we talk the spectrum, and we start with the real part of the spectrum. So I start with blue, and just draw the real part of the spectrum. And this example is not a concrete example so that I can basically easily draw the time domain signal. Yeah, it's not the intention. I just want to show, okay, let's say the real part would look like this of the spectrum. It would be Gaussian pulse, yeah. And we know this real part of the spectrum. If I know the right-hand side, I know the left-hand side. There is no new information, but we need the left-hand side to ensure the inverse Fourier transform gives a real wave signal. So we use complex waves. This looks like this. Should be exactly the same as on the right-hand side. So this is the real part of the spectrum. Now let's say we just write here A as the maximum value of this real. So and now we draw generic part of this spectrum. Basically, if I would draw the corresponding time domain signal, let's say we only have this real part in the spectrum, this would look like a Gaussian pulse multiplied with a sine or cosine with a very high frequency, so that you have an idea how does it look like. Now, draw the imaginary part. Let's say the imaginary could look like this. Imaginary part of the spectrum. We need to ensure in our figure, yeah, we need to ensure that the imaginary part, so this is x2 prime, is an odd function. No question about this. Therefore, here on the left-hand side, I need to draw this like this, yeah. So because it's the imaginary spectrum, since we know our time domain signal is real, it's to look like this if we know the right-hand side. So this is the imaginary part. So here B. Now you would say, yeah, it's quite easy to understand. If we delete the left-hand side, we still have the complete information because we can redraw the left-hand side if we know the right-hand side. The idea of this transform, and now I show here just this arrow just should show now we do a transform from a bandpass signal to a low-pass signal. This is just abbreviation from bandpass range to low-pass range. And we want to do a shift of the spectrum, and we want to do this shift to an useful frequency. Let's say it's this carrier frequency of our original laser diode. Yeah? Of course, the laser diode spectrum doesn't look like this. It's just, if it's a perfect laser, yeah, it's just in reality, it's one discrete frequency component exactly at this frequency. And if we talk about our two-sided spectrums, the same on the left-hand side. One very thin, yeah, spectral line. So, but now this would be a modulated signal because we have a certain shape in the frequency domain. So we have modulation. Now we do this transform with respect to a useful frequency. So for instance, that we have nice symmetries after this transform. And now we say, okay, sound? Is this really true? One person says there's no sound, and this would be really, oh, should have sound. It's okay. Oh, should, okay. I just saw this. Yeah. If you see some such thing, you can tell me because I don't look. I mean, you probably all you only you don't need get the chat as I. So now we do the transform, and the idea is make the signal especially in the time domain, as simple as possible. Don't look at this carrier. We know there is a carrier. There is an oscillation in reality, but we ignore it for our modeling. So we say, okay, we make a diagram, and this looks now like this. And this is everything in the so-called equivalent low-pass range. So this is, after this transform, this so-called equivalent This is the name for this. Then we have F here. Maybe just put this a little bit, say, here. So, and now, again, we draw the real part of the spectrum. We denote this with a prime, but we write here an index, L, for low-pass range. So, now if you would attend, for instance, my lecture in optical communication, since I do from the first lecture to the last lecture, everything in the low-pass range, I don't use this L, because everything is in the low-pass range. If you take a look at the book about fiber optical communication, everything is in the equivalent low-pass range. It's not even not mentioned somehow. Yeah, it's just, it is as it is. Yeah. And we draw, of course, this imaginary part in the same figure. Yeah, imaginary is with this 2 prime, looks like this. So and now, what do we do with the signals? We just say, we delete the left-hand side. You don't need an equation to do this. You can always use this graphical method. It always works. If you have you heard in this seminar about a Hilbert transform? Yes? Was it mentioned? Don't need this Hilbert transform to do this in an exam, for instance. Yeah? So you just delete this left-hand side with whatever component. You just say, okay, it's redundant. Then you shift the right-hand side, let's say, by means of this frequency Fc to the left-hand side. So this means now our spectrum is here. It has exactly the same shape, of course, yeah? Exactly the same shape as before. But now the new, let's say, center frequency is exactly 0. Here is 0, and what has been at Fc is now at 0. Quite easy. So this is the new real part, and then we draw the imaginary part. Right-hand side was positive, yeah, so it's still positive. Let's say here. Left-hand part disappeared. So now, I mean, I didn't use here the labels, here this A and this, sorry, B, yeah? But still, if one gives you this spectrum, okay, and he says, this is an equivalent low-pass range, and I've done this shift with respect to Fc, then you say, oh, then it's easy for me to obtain the original spectrum. I just use this, shift it to the right-hand side, and then the left-hand side, I produce the same with the complex conjugated symmetry. Quite easy. So you have all the information still in this signal. And now, let's say what we need to write here. Let's say if we write here A, yeah, we will somehow modify this. And if we write here B, we also might modify this B somehow. So this is not the whole story, I tell you. Yeah? Now we just want to take a look at the energy, because in this example, we discussed an energy signal, but you can also discuss the periodic signal, for instance, for the beginning. But we want to have deterministic signals at the beginning. So where we can mathematically describe exactly the time domain characteristic. Yeah? So now let's say we take a look again at the energy. The energy of this signal, we have calculated this energy first in the time domain. So it looked like this, right? We don't need a magnitude square here, because our time domain signal is real valued. Yeah? So it's just x squared to the dt. Yeah? This is the system theoretic energy. But now there is the theorem of Parseval, you know, probably, hopefully. Yeah, and you can obtain the same result in the frequency domain. So we just take a look at integral from minus infinity to plus infinity, x, sorry, of f, magnitude squared df. By the way, this is called energy spectral density, this x of f magnitude squared, but it doesn't matter. It's just theorem of Parseval, Parseval's theorem. See, have you heard about this? This is Parseval. So if I integrate over the magnitude square here, I get the same result for this energy. But it's important to use here this is magnitude, yeah? It's the absolute value, because we know our x of f is general case complex value. So we need to use this magnitude, this absolute value. And now you say, okay, if I only take a look at the right-hand side because I delete the left-hand side, yeah, I see the contribution. Look here, x of f is an even function. The magnitude of x of f is an even function. So if I put a square here and a square here, it's still even. So half of the contribution to this integral is from here and the other half from here. So I could write this a little bit different. So I could say this is integral from 0 to infinity. And then I write here x of f magnitude to the square df, right? And then here I put
I have a question.
Yes?
I have a, why are we deleting the left-hand side? Can you please tell me?
Why we delete the left-hand side?
Yeah.
Because we want to basically only end up with a spectrum which looks like a right-hand side of the spectrum because it contains all the information. Yeah? But we want to ensure that the frequency of this center frequency of this spectrum is, let's say, 0 or a different frequency which is very low, which enables us to obtain the time domain signals quite easy. So we don't want to have this oscillating characteristic in time domain signal. This is what we want to achieve. So if we go back in a time domain, these signals oscillate with this frequency fc, and this doesn't. We delete the left-hand side because if we shift the spectrum, yeah, we can shift the right-hand side to 0, but then this spectrum would be at minus 2 fc if we still have it, and this would help nothing because then the time domain signal is still complex, yeah, and still oscillates. So we want to delete this, but you will see it later in the examples. So now if I write this, yeah, 2 times this integral, it's the same energy, but I start with 0 because this spectrum here at the right-hand side would be just this would be just the original right-hand side. So now I can put this 2, of course, also before this x of f as a square root of 2, right? So if I weight this x of f as square root of 2, okay, and integrate from 0 to infinity, I get the same energy. And now, if we go in the equivalent low pass range, here in our university, this lecture, in many books, but not in all books, we do the transform like this, that we ensure the same energy before and after the transform. So, goal, same energy, or if we take a look at periodic signals or power, or for periodic signals, yeah, this example is an energy signal, clear power for signals. As before. So, I mean, I'm here in the equivalent low pass range and we want to assure the same energy. But since we deleted the left-hand side, now we just write here square root of 2. Don't forget to write this. And here we just write, of course, square root of 2. So we modify the original amplitude spectral density by square root of 2, and in order to ensure the same energy. That's the whole story, basically. Now you can do everything, yeah, means of this graphical method. Now let's take a look at a very simple example, and then we to a more difficult, slightly more difficult example. That just don't want to show exactly the same example, of course, as in the seminar example, or I have changed this to other years somehow. Let's say we have a signal x of t. And this is a very simple case of a bandpass signal. This would be just, if I take a look at the field strength, it could be the signal that is just emitted or generated by an unmodulated laser diode, a so-called continuous wave laser. So it has a certain amplitude. Let's say we call this amplitude x naught, yeah? And then let's say it's a cosine wave, cosine of 2 pi fct. Yeah? But in the seminar, I mean, it's always good to start this just with a pure cosine. Yeah? But let's say it has a certain phase phi naught. So phi naught is just constant, and fc is this carrier frequency. And f phi naught, yeah, is just, let's say, just like this. It can be 0, and to make it sense, we say it's between 0 and 2 pi. So if we have a certain phase, it could, then this cosine is mapped to a sine. But if this is in reality a cosine or a sine or a minus sine, it just depends on our zero, on our origin of the coordinate system. It's just an harmonic wave. Yeah? So, and now we know what is the Fourier transform of this. Yeah? And we use this graphical method to obtain the signal in the time domain. And I can tell you it's a constant. But look, this is really important, and we can write this. Now, the real part of this spectrum is even, right? Imaginary part of this spectrum is odd. Look, in this example, the real part is still even, but look at the imaginary part of the spectrum, which symmetry is still even. So this means the time domain signal in this exact example would be complex. So in the general case, the equivalent low-pass signal is complex. This is really important. I forgot to mention this. So XL of t can be, and in the general case, it is complex. So now we have complex valued signals. So this is the general case. Only in some special cases, the equivalent low-pass signal is still real value. So we cannot produce this completely with analog signal processing. Yeah? Signal cannot. So, and now let's take a look at the spectrum in order to find the equivalent low-pass signal, which is for some phases phi naught complex or pure imaginary, and for others it's pure valued. The simplest approach is the following. So rewrite this like this. So it's x naught by 2. And then I decompose this real valued wave to two complex waves, as we do with the Fourier transform, basically. So rewrite this is, I do it in 2 steps. E to the power of j, 2 fct plus phi naught. Then plus e to the power of minus j, ct plus phi naught. So we add 2 complex conjugated here and get a real number. And this is a cosine, right? And now we write this a little bit different. Maybe you just see the spectrum, how it looks like, but I just show you what's behind of this. Yeah? And then we could say this is x naught by 2, e to the power of j phi naught. This is a weighting, this is just a number. And then we have the frequency Fc. This is just a single direct delta pulse in the spectrum. This is our technical frequency. And then there is another frequency which is minus Fc, which belongs to our frequency spectrum. Yeah? So plus x naught divided by 2 is phi naught. So you see the phase is an odd function. Yeah? Plus phi naught minus phi naught at negative frequencies. And here we have the negative frequency. I write this like this. J, also there is a minus sign, 2 pi. And to show you, here we have the negative frequency. It looks like this. Fc is our real valued positive carrier frequency. Cannot reality negative. So this is a minus here. It's minus j 2 pi fct. Yes. Here. I mean this. It's correct. Minus j, and then the whole expression here. This gives minus g phi. It's correct. So, and now we do the Fourier transform. Again, you do not need to write this intermediate step. Yeah. Basically, if you would see the result, the spectrum looks like this. It's basically a x naught by 2 e to the power s delta of f minus fc. So there is a direct delta pulse at fc. And the amplitude is x naught by 2, because x naught was an amplitude, and this is the phase. So, and then plus x naught by 2. This is the complex conjugated. Then there is a discrete spectral component at minus fc. So for instance, example, say we assume phi to, say, plus 2. Assume this, and we draw a figure to do this, because we want to have a figure, and then we shift the right-hand side in this figure. But for a figure, I need to assume a certain value, otherwise I cannot draw this. Yeah? Say it looks like this. We have, see? This is f. Then here we have, again, this is the day where we use three-dimensional drawings. This is not as good as I want. To shift this to so, so now let's proceed. So this is bandpass range, of course. Yeah. Let's assume. Let's assume we draw here. I think green was the imaginary. Here we have x prime of, but three-dimensional, and then take a look at the frequency f. So here's f, c, let's say, at this frequency, and here's minus fc. So now let's think what happens. I'm not sure in which direction. So if this is pi by 2, then we insert e to the power of j pi by 2. Yeah? This gives, so here is a real part, area part. This is this angle, pi by 2, right? So this is just j, right? It's pure imaginary and it's positive because of this angle. Yeah? I delete this because this was not nice. Just, yeah. And then we could say, now our spectrum only has this imaginary component, or this phi, so it looks like this. So here we have a direct delta pulse, yeah? And there is no spectral component. There is no component which is real. Yeah? It's only imaginary because of this phase. So if this phase is plus pi by 2, then it's a minus sign. Yeah? It's minus sign for this case. x of t is equal to x naught cosine of 2 pi, also here in this example, for this phase, fct plus pi by 2. So we shift the cosine to the left-hand side, and then it becomes minus sign. Minus x naught sine of ct. So this is the spectrum, three-dimensional. Usually you don't draw this three-dimensional, but we can do this. Yeah? And it's like this. And this value here is basically just the magnitude. It's x naught pi. Because it's the imaginary part. Of course, it's also it's not. It's the imaginary part. J is before this x2 prime of. It's like this. This is our spectrum in the bandpass range. As you can see, we have this odd symmetry in the. Now we do this bandpass low-pass transform. So
Hello. Hello.
Yes.
Sir, kindly explain this phasor diagram once again.
What?
Sir,
Sorry?
kindly explain this phasor diagram once again.
This diagram. And this is just Fourier transform, and usually the Fourier transform is complex. And I just show in this diagram here on this x, this is just the imaginary part of the spectrum. This is the real part. Yeah. Since we only have an imaginary part for this signal, since it's this time domain signal, there's an odd symmetry. We don't have a real part of the spectrum. And if we would draw this for a different phase, let's say for phi not equal to 0, then here is a direct delta pulse which points up. Here is another direct delta pulse which points up. But you can see if we increase the phase, then these pulses begin to rotate in our frequency domain. This is just basics of Fourier transform. You can also draw two figures. One is magnitude and the other is phase. This is usually done, magnitude and phase. But I wanted to show this here, three-dimensional. So if you insert different phases, these direct delta pulses begin to rotate here in the frequency domain. But the real part is always, even in the imaginary part, is always odd. So, and now we shift this with respect to the frequency fc, and what we get is, of course, very simple, and we end up in this figure. In this case, it's really so simple that we don't need a figure. We can just with equations. Here's f. Here again, let's say this is x2 prime f, x prime of. But in the equivalent low-pass range, this is important. Low-pass range, this shift, and you see now this is exactly. What do we need to write? We need to write for this component, we need to write x naught by 2 times square root of 2, because we need to ensure the same power. And if we delete the left component here in the frequency domain, we would end up with half of the power. Therefore, we weight this with square root of 2, and we end up with x naught by square root of 2. So this means now our spectrum in the general case, I say, or we can say, what is this in the time domain, let's say, to this concrete example, what is it in the time domain? So we could, fx L of f is equal to, it's just, we don't have a real part for this example, for this phase. So we end up with j times, right? X naught divided by square root of delta of f. So there is only a direct delta pulse at f equal to 0. There is now our spectral component at the frequency 0. the amplitude is x naught by square root of 2 times j. And what is it in the time domain? Direct delta pulse is a constant, so it's a constant, but the time domain signal is now xl of t is just j times x naught by square root of 2. So the time domain signal is a constant. And what we see is basically the envelope of the original high frequency signal, x of t. So if we draw a figure for this, let's say we draw this, for this example, this, how does it look like? Minus sign, how does it look like if it's like this? So we can say, okay, do this, I don't know how to delete this and then just want to have this line style. So I want to draw a minus sign, okay? So t. So this is x of t. Remember, the phase is pi by 2 in this example. Now I draw a minus sign. It looks like this somehow. Yeah? Sign. This was the. And one period here is just c, of course. Yeah? So the period should be constant. This is not the best figure I've drawn ever, yeah? But you see it's a minus sign. So here, it's like this. It's not so easy on this tablet. It looks like this. So this is a minus sine wave in the it's not, right? So minus sign. So now I'm asked you, what is the effective value of this sign? The effective value. If the amplitude is x naught, what is the effective value? Is it x naught divided by?
By 2?
It's x naught divided by square root of 2. This is the effective value. What does it mean? It means the effective means if I would, instead of using this oscillating wave, if I would use DC voltage, let's say, what is the required voltage of this DC voltage in order to produce the same power, average power? And since the instantaneous power here is 0, this point here is 0, 0, here is it x naught squared. Average power is just x naught to the square divided by 2. And you see this in the effective value. So it means that x squared of t, I use this abbreviation. So we integrate the signal from minus infinity to plus infinity, time domain averaging, or one period. Insert x squared of t. This is, of course, the value to the square. This is the meaning, the definition of an effective value. This is, of course, x naught by 2. So this is the mean power of the signal. We say this is the power, power. So the mean system theoretic power. Now take a look at the power of this signal. Now we have a signal which looks like this, time domain. So it has only a real part, of course, generic part. Time domain signal, general case, it's complex, but in this case, we only have a real and imaginary part, time domain signal. So the signal looks like this. T, again, draw just, here it's positive value, just have this line, straight line. This is just an excerpt. Then we write here x naught divided by square root of 2. And here we write this is L2 prime show here, of t. It's just the imaginary part of the time domain signal. Yeah? So this is just xl2 prime t. This is our notation. 2 prime means imaginary part. Right? So what I've shown here is the imaginary part. So it's a constant. And you can see this is basically the envelope. Yeah? Oh. This bandpass signal. Envelope of this signal is a constant, right? Of the bandpass signal. The bandpass signal oscillates, but the envelope is a constant. And we see this envelope shape time domain. Therefore, we call this equivalent time domain signal also as the complex envelope of the bandpass signal. This is a different name. There are a lot of names, but sometimes you see also the name, this is XL of t. L of is also referred as also to as the so-called complex envelope. Of the original bandpass signal. It's a complex envelope. Here you see this envelope is basically says, how large is this oscillation? This is what we see in the time. Now look, what's the power of this signal? What is the power? XL2 prime of t. Now it's, XL of t. It's not allowed to just write square because it's complex. And now we need to use this and take the average. What is the average magnitude squared of this? If I square it, the imaginary part I get is not 2 to the square, of course. Here the square, yeah. Look, here, I forgot here a square side. Square the value, of course, the negative is not squared. But you see, it's the same power. And you see even more in the general case for this example, case, yeah. Then what do we get in the time domain? Look, general case, we have here this right-hand side spectrum. We just shift this spectrum from the right-hand side to f equal to 0. Then we end up, this is just substitute by direct delta pulse. So then we say XL of f is just x naught divided by square root of 2. So divided by 2 times square root of inner, right? Times e to the power of j delta of f. It's the general case. And what is it in the time? For general phase, it's XL of t is equal to e square root of to the power of j phi. Depending on this phi naught, sometimes we get a real signal for a cosine wave. Sometimes we get generic value for a sine wave. Yes, there was this acknowledgement from Ruslan Atakov. Of course, x naught squared. Chat. Very good, yeah, this is good. So, now we see it. Yeah. Our example, of course, yeah, we get this result with this j, but of course we can write this j here. This j can also be written as, let's say I do it here, is equal to, what is j? It has a magnitude of 1. It's just a phase. And the corresponding phase is pi by 2. So it's still x naught square root of to the power j 2. This is what we assumed for the phase. You can see the phase of this carrier in the yes. exactly. So we, let's say a little bit different, but you are right. Our time domain signals need to become complex, yeah, in order to distinguish between cosine and sine carrier waves. This is the reason. Yeah? The mathematical description is because we cannot ensure if we delete the right-hand side part of the spectrum, just shift this and delete the left-hand side, we cannot ensure that the real part of this spectrum is an even symmetry. This is just in this example. And the imaginary part has an odd symmetry. Let's say even this spectrum, yeah, if the real part would look like this, just for an example, if this is the real part of the spectrum, then on the left-hand side it would look like this. But if I shift this now to the left, and then this is the center, it's not even. Then in this case, again, the time domain signal would be. But still, it's easier to calculate with this, much easier than to always consider this oscillation, yeah, system. And now want to go back. We start with the time domain signal, go in the frequency domain, get for the first an equation, but this equation shows a so-called quadrature modulator. See, this is used in practice. It's really important what we do now. So we do it with an example, a second example. So we start in the time domain, yeah. Second example. And go in the frequency domain. But we want to do this. You can always do this graphically. Do the Fourier transform. You put the Fourier transform on shift it to the right-hand side, produce the same complex conjugated left-hand side. But we want to start with, let's say, a signal which looks like this. XL of t. So we start in the time domain, yeah? Okay? We say, okay, the time domain signal would look like this. Minus j seems to be something like a sine wave, probably. But we will see. Minus j, say, x naught, or say b. Just write it here. It's a value. It's a certain value. Rect t by t. So this is our time domain signal. We want to find goal. Look for x of t. What is x of t? We assume that the carrier frequency, which we used for this transform, was large compared to this 1 by t. So this means, yeah, here we have a rectangular pulse, yeah, and the width of this rectangular pulse is huge compared to the period of this original wave, just for our drawings then. Let's remember optical communication. Let's say this capital T is 1.0 nanoseconds. This is a tiny value for 10 gigabit per second on off keying. The carrier frequency is this femtosecond, 5 second. As the reciprocal value of this carrier frequency. So the period of the optical carrier. This is ensured, oftenly, even in radio frequency transmission. So now, how can we obtain very efficient time domain signal in bandpass range? Well, so this is basically the inverse transform what we are looking. Yeah. So this is the inverse bandpass low pass transform, because it's a low pass to bandpass transform. So we go back. Yeah. So this would be the inverse. Now look, how could we do this? And I just show a figure. I don't show a figure, I just show the equations. So we could say, if we do this, the first step would be take the original spectrum, shift it to the right. So now I say, okay, I could say, in the time domain, what do I need to do in order to shift the spectrum to the right-hand side? I need to shift this to the right-hand side. What theorem is needed if I have a frequency shift, or this corresponds in the time domain, because this theorem is called, it's the shifting theorem. You know, I just write it here, let's say. Yeah. And then I delete this. Yeah. If I have, say, x of f is in the time domain, let's say x of t. Then if I take a look at x of f minus f naught or whatever, yeah, I shift the spectrum. If this f naught is positive, I shift to the right. Then in the time domain, I get x of t times e to the power of plus j 2 pi f t. So I need to multiply the complex wave with the frequency f naught. So this is shifting theorem. So this means if I want to shift this low-pass signal frequency domain to the right-hand side, I need to multiply with e to the power of plus j 2 pi fct. Of course, I need to know the original frequency used for this shifting. So now you may say, I need a further step on the right-hand side because before I multiplied with square root of 2, so I need now to divide by square root of 2, right? So, and this corresponds, if I now would do the following, if I now would go in the frequency domain, this is just the right-hand side of x of f. Of the bandpass signal. And then it's clear what I have to add in order to obtain the left-hand side. I only have to add the complex conjugated. Because if I have two complex numbers, they become real if I add the complex conjugated. This gives the left-hand side, the spectrum. So then it's clear I just have to add this. Plus xl of t times e to the power of j2 pi ct. And I write it like this. It's conjugate. It's the left-hand side. I don't write it because it's clear. But then the time domain signal becomes real valued. Only if I have the original signal and then I add the complex conjugate, I get the original signal. And the square root of 2 is already obtained. So, and if I do this, I have now an important equation which describes this inverse transform. This is this, x of t, so in the bandpass range is just, if I have a complex number and I add the complex conjugate, get 2 times what remains is 2 pi, it's the real part. So what remains is 2 times 1 by square root of 2, so it's square root 2. Then real part of xlt is e to the plus j ct. This. Yeah. This is the first method, yeah, to obtain the bandpass signal in the, say. We could use this equation for our signal here, then we can obtain the signal. But, I mean, we only have to, okay, we insert this now. Let's insert this. Insert XLT. Now let's say we do this. You see, it's pure imaginary here. Okay? So we insert this. So therefore, x of t is equal to, for this example, square root of 2 times real part of, so what is the example? Minus j, just minus j times b. It's an amplitude, yeah, times rect t by t. This is xl of t. It's complex in this example, times e to the power of plus j c t. Question is, what comes out? Then a good idea is, then so 10 minutes and we end up with a very important schematic. Say this is cosine of ct plus j times sine 2 pi ct. Okay, now let's look. At the end, we take only the real part, only the real. Here we have a j, but j times j is, it's -1, and then we have here this minus, it's +1 at the end. But cosine times j is, it's imaginary, it's not real. So this means we know the result. The result is, in this example, square root of 2 times b. There is no minus anymore, because minus minus 1 times rect t by capital T times sine of 2 ct. So this is the equivalent signal. The bandpass range is a modulated sine pulse. Maybe we draw a figure. Yeah, it looks like this. Sorry. You know how it looks like. Yeah. Want to draw this? This example. And you see, it's much easier to draw the signal in the equivalent low-pass range than to draw the signal in the bandpass range. So here we have T. We have a rectangular pulse. Let's say it extends from here to here. This is this rectangular pulse. And this rectangular pulse, during the duration of this rectangular pulse, the signal is switched on. Otherwise, it's switched off. So here we have an amplitude which is square root of 2 times b. Why? For same energy, but now the signal oscillates. Then we have a sine, and this looks like this. Yeah. So this is our signal range, which belongs to this signal in the range, which is just a rectangular pulse with a certain phase. Sorry for this drawing, but you can see what happens. You see, it's much more difficult to draw this in the bandpass range. Yeah? Time and so on. This is x of t. So, but now, 8 minutes. Now we want to further take a look at this expression. Let's say, again, we take a look. So this is equation 1. So I write here, this is equation 1. Okay, and then 1 can be written as. So now we do the following. It doesn't make sense. So we say XL of t, our time domain signal, has a real plus an. So this is our notation of distinguish real part and generic. It's a short notation. Yeah? Then we said what we use here, we say e to the power of plus j ct. This can be decomposed in cosine of ct plus j times sine ct, right? It's just, instead of this, we can use cosine plus j times sine. Now we take a look in this expression, here in the 1. Real part of this times this. So we need to multiply upper signal, let's say. Yeah. We multiply this with this and take the real part of what comes out. X of t is equal to, of course, square root of 2, right? Because we need the square root of 2. But then this times this is real, right? This times this, there's no j. So we can say there is a signal. We say this is the real part of our complex signal, which modulates a cosine carrier. sine of 2. Cosine carrier becomes modulated. It's a signal, an analog signal. This can be interpreted as the real part of our complex signal, but this is just an interpretation. And then look, this times this becomes imaginary. So it's this j, but to take the real part. So there is no combination of this and this. There's also no combination of the cosine carrier and this, because this is a j. But here we have j times j. This times this becomes -1. So this means we end up with this minus square root of 2 xl2 prime of t times sine of 2 pi ct. So at the same time, to generate a general bandpass signal, we can modulate a cosine and at the same time a minus sine wave. And we say that these two carriers, so including this minus, but this is not so important. So even if you would modulate, just show it here. Usually this belongs to this. We say, since there is a 90-degree phase shift, so if I have a cosine and shift the cosine by 90 degrees, it becomes a minus sine, right? All this quadrature carriers. And quadrature does only mean 90 degrees, nothing else, okay? And the engineer denotes, often he denotes xl prime of t as the so-called in-phase component. So this is always the component which modulates the cosine part, the cosine carrier, yeah. And the other xl2 prime of t is called it's the so-called quadrature part component. There are two carriers in quadrature. One is the in-phase and the other is a quadrature. Quad 2. Now we can draw a figure to show how can you obtain a bandpass signal. This is used in practice to transmit data. If you transmit data very efficient, you can use the so-called quadrature modulation. In this case, you transmit one data stream by modulating a cosine carrier. The second data stream, this represents an analog waveform which represents discrete data. Yeah. This modulates a minus sine carrier. So, and this type, let's say, if we show this as a figure, looks like this. So, yes, exactly. And then this is section 1, section 1, and here you see this as a figure. This is the so-called, or let's say, quadrature up conversion, because we have two signals which have let's say, center frequency of 0. These are low-pass signals. Let's say these two signals represent two data streams, analog signals, real-valued, two real-valued signals. Yeah. Cannot simply add them. You cannot say xl prime of t plus xl2 prime. Only allowed to do this with a j in between. So this need to be digital versions of this, numbers. Yeah. We sample this and this, take the samples, we can put j in between, because then we have numbers. We can operate with digital signal processors, with these digital numbers, but not with analog circuits. Here in this circuit, we have a cosine carrier, and we delay this cosine carrier. It's just a carrier, a sinusoidal carrier. And we delay this carrier by 90 degrees. And if we assume that this is a cosine, then this becomes a minus sine. In practice, this is just an oscillator. and we delay this signal by a time amount which corresponds to a 90-degree phase shift, and then we get these quadrature carriers. And then we modulate this cosine, we modulate this minus sine. If we add both signals, we have the bandpass signal. Of course, in some cases, you only modulate one carrier, not both at the same time. Since we shift the spectrum to higher frequencies, we call this upconversion. This is so-called quadrature upconversion because we do this with two streams in quadrature. And you may say, okay, the bandpass low-pass transform, there's also a circuit. We do this in the next lecture. Yeah? This is quadrature down conversion. And then we receive an RF signal. I just show it here, and in the next lecture, you will see why this works. So we receive a bandpass signal in practice. Again, we multiply with these quadrature carriers, but we need to do this, or we do this for a down conversion. Down means, we go from these high, huge frequencies, let's say if it's Wi-Fi, 2.4 gigahertz, then we go to 0 gigahertz, But then we have two output signals. One can be interpreted as the real part of a complex signal and the other as the imaginary part. But both signals are real, continuous time at this point. And then if we plug here an analog to digital converter, here an analog to digital converter, this is important. Then we have just samples. Then we can, the samples which correspond to this, multiplied with a J, then we can add both. If we plug a J here to this part, but this is only possible in the digital domain. If we just operate with numbers and signal processors. This is down conversion. So the idea is to have data, for instance, in the low pass range, low frequencies. We can use digital generation of these signals. Sorry, this is down conversion. This is the band. Sorry, that's wrong. We are in the bandpass range. Then we do down conversion, and then usually here we have an ADC, here we have an ADC. Then we do the processing truly with complex signals at a much lower frequency range, which is good for technical realization. Okay, that's all. See you next.
Hello, sir. For providing 90-degree phase shift, do we use Hilbert transform here?
You need again to increase the distance to a microphone because there
Okay. Sir, for providing 90-degree phase shift to the sinusoidal signal, do we require a Hilbert transform here?
No, we don't need a Hilbert transform. There is a possibility to obtain the equivalent low-pass signal also by Hilbert transform, but this is the much more, I mentioned this in the next lecture, but this method is much more important. And why we need this 90-degree phase shift, because we see this in our equations. This is one argument. The other argument is, if you want to have another mathematical explanation, is that the cosine and the sine, they are so-called orthogonal signals. Cosine and a minus sign, they are orthogonal. So like two vectors which have a 90-degree orientation, and if they have a 90-degree orientation in a two-dimensional space, area, then they are orthogonal. This 90-degree phase shift means that if you multiply the cosine with the sine, time domain, if you integrate over one period, the result is 0. This means these two carriers are orthogonal, otherwise it wouldn't work. This is another explanation. But this is...
So with oscillator, we are using some different circuitry, sir, to achieve this 90-degree phase shift.
Sorry, it was too loud. It was too loud.
Sir, I'm saying that with oscillator we are generating sinusoidal signal. So do we require additional circuitry for this 90-degree phase shift?
We only need one oscillator, yeah? And then
Okay.
we shift the signal what comes out by a certain time, which just corresponds to this 90 degrees. Yeah, it's of course one oscillator. Never use two oscillators in practice, because especially if you generate this analog, yeah, analog oscillators, they never have exactly the same frequency. So, and therefore you use basically one oscillator. I just show you if you want to draw this. You can even do this in optics. Let's say you have one oscillator, yeah, but then we want to stop oscillator. I hope this is correct. Oscillator, is this written? Oscillator, yeah, and there comes an harmonic wave, but you don't know if this cosine or sine. It just depends where is the zero, where is the origin. It's the time zero. Then you say, I split this up. Yeah. Then I make here a time shift of t naught. With this time shift, the time shift is just 1 by 4 Tp, or 1 by 4, F naught, yeah, which is 1 by 4 Tp. So the period of this carrier, let's say, is Tp, which is 1 by F naught. If I introduce a delay, which is a quarter of a period, a cosine becomes a minus sine. This is the whole story. So now you have two oscillations, but for this frequency, F naught, or FC, we always used FC, yeah? FC, this is the carrier frequency. If this is the carrier frequency, FC, I introduce a delay of T naught, then I get a so-called quadrature pair. Yeah? Then I use multiplications. Yeah? By the way, nowadays, usually don't do this in one step. You usually say, I first realize the whole schematic here in the digital domain. So this FC is, let's say, not 2.4 gigahertz. Let's say it's only 100 megahertz or so. And then you have possibility, since the carrier frequency is so low and the bandwidth, the signals are so low, that you can realize this time shift very precisely, for instance, very precisely, because everything is digital. And even the multiplications are realized in the digital domain, so everything is absolutely precise. Then you basically have an upconversion in the digital domain, sampled signals, to a center frequency of, let's say, 100 megahertz or 200 megahertz. It depends on your bandwidth. Yeah? And then in the second step, the final analog upconversion. So you use digital to analog converters, yeah, to obtain two, of course, signals. Yeah. So I do the upconversion here, but this can be digital. So here we have x prime t, x2 prime t. Yeah. So I don't need to write here the square root of 2. This is just for our modeling. Yeah? So, and then we have two signals, and then we use here digital to analog, basically. Then we have here signals, but the carrier frequency is still very low. So, and then, sorry, this was nonsense. This is upconversion, right? And I need to add both, yeah? And then here I have this digital to analog conversion. And then I do a further upconversion here, just by multiplying with another harmonic wave. And this makes the final shift in the frequency domain, let's say, to 2.4 gigahertz or so. So we first upconvert to, let's say, 200 megahertz, yeah? And then to 2.4 gigahertz. But then we only need the at this point, for this analog. So this is digital because the frequencies are so low. And then we do a second multiplication here. Now I need to multiply because we have only one real valued signal. Yeah, and we shift the whole spectrum, which has an imaginary and a real part, just to the final frequency. I call this F delta. It's not FC, it's F delta. Yeah. So we do this in 2 steps. And do you know how this is called? Such a modulator? Do you know the name? Or do you know the name for the receiver? If you do this in 1 step, you call this in practice homodyne. This is heterodyne, super heterodyne, sometimes in RF. So this structure is called super heterodyne upconversion. If you do this in 2 steps at the receiver, which is usually done, you call this super heterodyne detection. You can Google in Wikipedia, super heterodyne detection. Yeah. Just do everything near the 1 step. Yeah. The reason is you want to use digital signal processing. Yeah. You want basically perfectly 90-degree phase shift here. And you cannot ensure this in the analog domain. If you do this in the analog domain, it's often said that you have an imbalance between the quadrature components because the realizations are not identical. And the multipliers here are not. Then you can change, if this is digital, you can even change the frequency somehow. Then you remember, if you do Wi-Fi, you transmit at different carrier frequencies. Then this frequency is usually fixed. This is just one analog oscillator with a fixed frequency. And then you change this first upconversion. You change digitally the frequency. This is can easily be done. Then you can realize, still perfect delay here, obtain 2 orthogonal carriers, but you can do it with 1 circuit for different frequencies. If you take a look at the Wi-Fi, you have really different carrier frequencies. I hope this answers a bit. Yeah? But anyway, we cannot discuss everything. We have to say, okay, this is our model. We can calculate with this, but I cannot present you all the technical details of quadrature modulators and demodulators. Then we need 1 lecture for this. Yeah. Exactly. This is good denoted what we basically, if you build such a modulator as shown in this figure, if this is digital, you call this quadrature amplitude modulation, QAM. QAM is the most famous modulation scheme, and this would be a modulator to realize this QAM modulation. QAM is the most important modulation scheme. There is no other modulation scheme which achieves this energy efficiency for a given bandwidth efficiency, because we can transmit 2 data streams in parallel, one which modulates a cosine and the other which modulates a sine. It's a percent of the nature. Yeah, this is just the idea. You never lose the phase. Yeah, if you insert a different phase, this is shown here in this example. You never lose the phase. You have in the frequency domain, you have this. So this is frequency domain. You see the phase in the low pass range. So you see the phase, and in time domain, you still see the phase because here it's the phase. You never lose the phase. As I said, in the next lecture, I show you a schematic which shows a practical schematic to do this. I closed the presentation. The thing is, if you do this analog, you can say, I have this quadrature down conversion and I obtain the real part of this complex signal, which we denote as the in-phase component. So I just obtain the in-phase component. And separately, I obtain the quadrature component by this analog circuit. Yeah? And then if I would say, if I just draw a figure here on my board, I can say, now I take this and add plus j times this. But this cannot be realized in the analog. But what I've shown in the figure is the real world. This is realized by schematics, yeah, in the analog domain. And then usually today, if you build such a homodane receiver, you sample, let's say, the signal which is down converted with a cosine, you sample this and put this on an analog to digital converter. Then the signal which is down converted with the minus sine wave, so with the 90-degree phase shifted, again, and to digital converter. Then the whole processing after these two analog to digital converters says I take the one signal, digital, numbers, 1, 2, 3, and add plus j the other, and then you have the complex signal. But complex is always digital. This is reality. And I just told you again, look in Wikipedia, we cannot spend too much time. Yeah? Take a look what is a super heterodyne detector, and then do this down conversion and up conversion, yeah, in 2 steps. Just to a so-called intermediate frequency as a first step, and then this is reality. But this is a whole lecture. How do I Of course, because the signals which go on air are real. Never have complex signals, never. If you have a measurement test equipment, yeah, testing sensor, yeah, signal which you can really measure, yeah, is really weak. I've never seen a minus j. So there is no minus j which comes in the microphone. It's just the pressure of the air. There's no j coming out of the antenna. It's a signal. There's no risk that there is a square root of minus 1. So thank you.